Our nice linear models have provided a powerful foundation for building predictive models. However, they're sometimes too rigid for the situation at hand. In this video, we'll explore another more flexible, non-parametric alternative, the LOESS, or local regression algorithm. Recall an example. Our goal here is to build a predictive regression model of Y, a subject's blood glucose level in milligrams per deciliter, by X, the time in hours since ingesting a high carbohydrate meal. We represent this predictive model by Y equals f of x plus a residual error epsilon. We've learned that we can build a flexible approximation of this trend function f of x using the non-parametric k-nearest neighbors algorithm, or KNN. Now, KNN is nice in that the algorithm itself is pretty intuitive. It puts into action the idea that data points with similar x values should probably have similar y values. However, KNN also has some drawbacks. First, as we've observed, KNN produces blocky, unsmooth models. Not only can these be difficult to interpret, they often misrepresent the smoother relationships that we're trying to estimate. Second, when we're working with lots of predictors, thus working in high dimensions, the distances between observations, even within the same neighborhood, can be quite large. In turn, the quote-unquote neighbors might actually be quite dissimilar. This phenomenon is called the curse of dimensionality. Local regression offers a more nuanced and sophisticated non-parametric regression approach. There are various approaches to local regression. We're going to focus here on the locally estimated scatterplot smoothing algorithm, or LOESS for short. Let's start by considering how this algorithm would predict the typical glucose level 35 minutes after eating. Now, we didn't observe any data at this time point, but the local region can provide some insight. For example, we can narrow our focus to the 3 nearest observed time points here. If we were using the KNN algorithm, we would then predict the glucose level at this time point of 35 minutes to be the average glucose level of the 3 neighbors. We do something similar, though slightly more nuanced, in the LOESS local regression algorithm. As the name suggests, we fit a local regression model to our neighbors. We then estimate from this model that the glucose level after 35 minutes is roughly 5.75, represented by the red dot here. We could similarly approximate the glucose levels after 3 hours by fitting a local regression model to the 3 nearest observed time points. Represented by the red dots, we've now estimated our model function f of x at 2 time points. We can similarly get local estimates of f of x at each time point x. Connecting the dots between these estimates produces a smooth approximation of f of x, hence the term scatterplot smoothing. Again, every point along this smooth curve represents the local regression estimate at that corresponding time point. With the big picture in place, let's step back and consider some details. In building a LOESS model, there are 3 features that we have to consider or tune. The first decision to make is what type of model we want to build within each local area. Though we'll continue to stick with a simple linear trend within each area, we could use a quadratic or even higher polynomial trend. Second, we must determine how much weight to put on each observation within the local area. The idea here is related to Tobler's first law of geography. Everything is related to everything else, but near things are more related than distant things. In the context of LOESS, this means that in building a local model, we should give higher weight or influence to the closest or most nearby data points. Mathematically, these weights are selected or defined using a kernel function. We won't get into kernel functions here, but I encourage you to do some digging. Finally, in building a low-S model, we get to choose the span, or quote-unquote size, of the local area. This is similar to the idea of having to pick the neighborhood size k in the KNN algorithm, but the math is a little different. Mainly, the span tuning parameter indicates the fraction of data points that we want to include in our local area, hence our local model. So it's the fraction of data points, not the number of data points. As a fraction, the span can then range from 0 to 1. When the span is near 0, our local models are using very few data points. And when the span is 1, our local models use all of the data points. To explore how the span can impact our low-S results, let's consider some examples. Let's start with a small span of 0.15. Recall that we have 14 total data points in our dataset. Thus, when predicting glucose at any time point, the local regression model will use only 15%, or 2, of these data points. This is a really small window. Not surprisingly then, by giving all influence to just the 2 nearest data points, our model appears overfit to our sample data. The resulting low-S basically just connects the dots, picking up the local noise that we don't expect to translate to every person. Moving on, let's increase our span to 0.5. The corresponding low-S algorithm thus builds its local regression models using the nearest 50%, or 7, of the 14 data points. By taking more data points into account, the local data points no longer have an outsized influence on the model. As a result, the model is smoothing out and picking up more of the general or global trends, as opposed to picking up the local noise. If we build local models with the nearest 80% of data points, that is even more data, our model smooths out even further. And of course, we can take this too far. If we use a span of 1, or 100% of the data points in our local regression models, we'll begin to ignore the local trends entirely in favor of the general or global trends. Considering that we're using all 14 data points and simple linear regression models within each local area, you might have expected the resulting low-S to be a straight line, not a curvy model as we observe here. This curvy nature is explained by the weights that we assign to data points in the local area. Mainly, even though we're using all data points to predict glucose at each time point, we're giving more influence or weight to the observations at nearer time points. As such, we do still pick up some local trends, but they're just pretty muted. Zooming out, let's connect these observations about the impact of the span tuning parameter to the bias-variance trade-off. First, we observed that when the span, thus our local neighborhoods, were too small, the low-S model was too flexible. And we know that, though extremely flexible models might enjoy low bias or good predictions within any sample, they'll suffer from high variability. That is, our small span low-S results can change a lot depending upon what sample data we happen to get. At the other extreme, we can pick a span, thus a local neighborhood, that's too large. This produces an overly rigid model that loses the local trends. And though a rigid low-S model will be stable and won't vary much if we use different data, it's also greatly biased. Its predictions and depiction of the trend within any sample tend to be off by quite a bit. Thus, to win the bias-variance trade-off, we want to tune our span parameter just right. We want it to have low variability or be consistent from sample to sample, while still maintaining a sufficiently low bias. In closing, the final slide here lays out the low-S algorithm all in one place for your future reference.